The amyloid hypothesis is dead. It is just dead. Everything has been, as you showed, a knockout blow. It's just like I said, the very experiments on origin of life scream out that it didn't happen this way. It happened somehow. But as far as scientifically what we know, we have no idea. This is why I keep saying we are clueless on the origin of life. And everybody says, oh, no, we're not clueless. What are we confident about? So we're here again today with Dr. Royal Truman, who's a PhD organic chemist, and also he's done a lot of theoretical chemistry around that, computational chemistry, I should say, around that, having worked for BASF, which is a very large chemical company in several places of the world. He's worked for them, and he's been on the program before. We're going to talk about part 2 of the amyloid hypothesis, this idea that amyloids, these polypeptides, which are proteins, which are a string of amino acids, could somehow have been the beginnings of life forms. And so he's taking us through some of that. We covered some of that in part 1, and we're going to move into that now in part 2. Welcome, and thank you for being with us again, Dr. Truman.
Yes, thank you very much, Dr. Du. I had a really good time last time I was here. I'm going to talk today about whether it is plausible that these kinds of amyloids may have realistically existed at all prebiotically. I mean, if they didn't exist at all, and there's just absolutely no possibility, then we shouldn't spend a whole lot of time on these kinds of discussions. So, overview then, let's talk a little bit about the requirements that all peptides or proteins must fulfill for life to be possible. It's very important to understand and quantify that peptides like DNA and RNA and virtually any big biomolecule hydrolyze in water. Big problem. And the big part is going to be to quantify and explain how important it is not to overlook that very special sequences are required of these short peptides to form amyloids. And to understand this, we have to look at some of the origin of life experiments that are supposed to tell us what kind of amino acids may have been present in a theoretical prebiotic world. So what kinds of amino acids, specifically their proportions, are found in the Miller-type experiments, and some very important work that just came out about the most plausible source of amino acids at all, and also the meteorites. So it's important to understand that peptides and proteins must fulfill many purposes simultaneously to be relevant for origin of life purposes. When we look at origin of life papers, what is being done? Sometimes experiments are done at hydrothermal event type conditions, very high temperatures. Other times, the experiments are done in icy water type conditions. There's a reason for this. It's because the researchers are focusing on some particular aspect, some feature of these peptides or proteins has to be met. And each one of these features can best be met under specific conditions. Unfortunately, meeting all of them is mutually incompatible. And it is easy to show that by emphasizing one particular feature, let's say you want to obtain the largest, longest peptides possible, the conditions that do that are going to automatically mess up other properties. For example, they're going to automatically accelerate the rate of racemization or will facilitate the amount of other products, chemical products that can occur at the ends of the peptides or in the side chains. So all these requirements are mutually compatible, but they must all be met. So I'll quickly overview what are the 10 requirements. First of all, a bunch of amino acids must be linked together. In the case of proteins, very, very, very long. In the case of the peptides that we have been discussing for amyloid purposes, not so long. But many amino acids must be linked together. Only the L form must link. You want to form only the linear and not a branched mixed mess. You need precise sequences of amino acids and not random ones, and then to be able to form useful functions. So specific sequences only. Other molecules, including non-biological amino acids, have to be avoided. These chains must adopt suitable three-dimensional structure reproducibly. And whatever is formed successfully, many copies must be able to form and also reproducibly and continuously for millions of years. In other words, one lonely little correct protein structure in the Antarctic survives for 32 seconds. It's not going to do any good. So you've got to have some method of creating many identical copies. And you need the correct proportion of the peptides. We're not talking about the amino acids, but whatever these peptides are, they have to interact. They have to have some kind of a lifelike network that interact together, and they must be co-located. This whole system now must self-replicate at some point. And the whole thing, of course, must be produced under relevant conditions.
Okay, let me just interject one thing here. We went through this thing of this list of 10. None of these has ever been done in a prebiotically relevant experiment. Not a single one.
That's true.
You know, you need
We're having fun, aren't we?
You need a 300
we're having fun, aren't we?
And people have made like up to 14, and that's with you're going to get branching. And so even the 14 MERS that they've made are ridiculous because they usually didn't have any of the ones with the active side chains. Only getting the L amino acids, nobody knows how to do that. The linear forms will never form. You always get the branching. Number 4, the precise sequences. There's no precise sequences. It's always random garbage that they get. Other molecules have to be avoided. There's no way to do that in prebiotically relevant experiment, but chemists will always make it so that nothing else is around until they want it around. So the long chains must adapt to three-dimensional structure without chaperones for most of them. That's very hard to do. The vast number of peptides have to be copied for millions of years. They can't even get the copied once, not even once. And the correct proportion of peptides have to have a specific sequence and must be co-located. No one's ever done that. The entire system or organism must self-replicate. Never been done. And this three-dimensional structure under relevant conditions never been done. So I guess there's your whole list. I mean, I just gave you the answer. None of it's ever been done.
Boy, you've just ruined my whole talk.
If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus.
No, but what I want to do is I want to quantify these things, and I want to show that these things can be demonstrated chemically. I don't want people saying, "Yeah, we just haven't found the right conditions or we're making progress." No, I want to put things in the proper perspective. This can be done scientifically. Now, why are we talking about the amyloid world at all? Well, there are some features that allegedly could simplify some of these requirements. So these are the 10 requirements again. Here's one. People are saying or thinking, if we can find little peptides that are able to form amyloids, and these peptides are only, 4 to 7 long, hey, that's got to be a lot easier than forming, let's say, a 300 amino acid protein, right? So they're saying, hey, hey, this could be kind of a step in the right direction. So this arrow upwards says, okay, fine. As you go through the discussion, this is going to be something that could be easier than other models. Okay, so up means, okay, fine. The amyloid world would have that benefit, and the down arrow says, yeah, but you know what, guys? You're going to have other problems that make matters even worse. So this basically means this requirement is not being addressed by the amyloid world hypothesis at all. And I'm not going to spend a lot of time discussing about whether it's going to be more or less difficult than, let's say, starting with a protein-only scenario or not. I don't want to do that. We don't have time enough. But I do want to talk about two other considerations that actually are very, very problematic, and even more problematic for the amyloid world hypothesis than other models. First of all, you need very, very precise sequences. If you're going to get these beta sheets, you can't have here and there things that are messed up. In a huge protein, you could have a little more tolerance. It could be places here and there where an amino acid's been substituted, still work. Unfortunately, here, these sequences, if you're going to get down to 4 to 7 amino acids and still get amyloids, you are talking about some very, very precise, pure sequences. And perhaps my favorite, because it's never discussed, you've got to have an enormous amount. Look, if you want to talk about other models, you could argue that a low concentration of an enzyme might be of some value. You can't argue that with the amyloid world hypothesis. You've got to have an extraordinarily high concentration or you don't get the amyloids to form at all, okay? It's like crystals. You don't get two salt crystals separated by 1,000 kilometers looking for each other and slowly building a crystal. It's got to be high concentration at the same time and place. So these are the things that I want to limit myself to, and I'm going to demonstrate that the whole hypothesis is pretty hopeless. Let's take a hard look at hydrolysis of peptides. Here is what's going on now. If you start off with an amino acid, get a dipeptide, tripeptide, etc. This whole equilibrium favors hydrolysis, not condensation. It's all going the wrong direction.
I'm going to point out to people the arrow going to the right is very small. The arrows going to the left are very large, meaning that it favors the left side. And so you've got favoring the left side all the way along. And
Right.
plus he's only got a very simple amino acids where he's not worried about the side chain coupling.
That's right. So we're talking, because there are 10 independent requirements, we are only going to talk about the length of the polymer in this presentation, and the other things like racemization, the side chains, are other problems that we're not just discussing. We're only interested in how much of larger peptides would exist at all. That's all we're asking. And that's a very important question because it puts things in perspective. And this can be quantified. I've done this. I mean, this can be done. And this is what I want people to understand. Let's look at thermodynamics. The way it works in water is if you start off with a dipeptide, real small, it hydrolyzes. That means it's exothermic and goes down here. So in these kinds of studies, this is what you do. You don't try to go from two glycines the other direction simply because you haven't got all the time in the world and you die before seeing anything. You do the opposite. You synthesize in the lab this, and then you allow it to equilibrate, and then you do your kinetic studies. So what's happening here? If you have a dipeptide, it is very exothermic. If you start off with a tripeptide, it's also exothermic, but not quite as much, okay? And Chemists know this. Dr. Truman knows this. This forms a suitor ion here. Both ends of the glycine are charged. It forms very strong bonds in water, and it's very, very stable, and that's why this is a very exothermic reaction. Once these things get larger, they're always exothermic, among other things, because you end up producing products that themselves are stable in water, but it's not quite as dramatic. So
you're producing more. You're breaking them up. I mean, so
right.
you're
Entropy.
Entropy. So
Right.
he's got free energy that gives free energy. So this is
Correct.
not just enthalpy; it's got entropy built into it.
Correct. So here are the rate constants. Now, there is very, very little data on these kinds of studies because chemists know this. You know that this is a hopeless reaction. You're not going to get a paper out of publishing this kind of stuff. Everybody knows this. What little work is done with glycine simply because you haven't got all these other problems that Dr. Tudor alluded to, branching, side chains, that kind of stuff. But who cares? Glycine is by far the most plenteous amino acid that would have been present anyway. So who cares? So here are the rate constants that are available at 25 degrees, for example. The rate of hydrolysis is about 100 times faster than condensation, which is also true at roughly at higher temperatures. If you compare 140 degrees, the rate of hydrolysis is faster. That's the rate constant. And that is, keep in mind that hydrolysis means the peptide itself plus water all over the place. Water is fixed concentration, more or less. So there's a unimolecular reaction, whereas condensation requires either two peptides or a peptide plus an amino acid to condense. It's a bimolecular. So it's obvious now from the rate constants why hydrolysis is going to be favored. Okay, but I wanted to quantify this because I want to put some real numbers on this so people finally wake up and see perhaps we should stop wasting time on things that are hopeless. This is now a published computer model that I, with some friends, worked on. Here are the results that we got using the rate constants at 25 degrees. What's happening here again is we're slowly building up the larger peptides until you've got the dipeptide, then no tripeptide can build. It's got to go sequentially. That's why when you look at the computer plots, to go all the way down here to the bottom to the nonapeptide, you see right here at the left end, there is none initially, obviously, because it's got to build up first from the smaller ones, right? But what is remarkable is that it reaches equilibrium a lot faster than I would have assumed before I saw the rate constants. That means that hydrolysis occurs very, very rapidly. So once you get enough of the peptide, it hydrolyzes so fast that you reach a plateau here. It just doesn't get in, the concentration doesn't increase. So for each one of these plots here, there's a slight time lag to the right as you get to the larger peptides. The larger ones rely on the smaller ones forming first, but you've got to also look at the y-axis. These are very small numbers. Now let's look at the numbers that we came up with. We got the exact same results using our kinetic modeling and the thermodynamic predictions, exactly the same numbers.
Because of you, millions of people have heard the gospel. If you confess with your mouth Jesus is Lord and believe in your heart that he's risen from the dead, and you will be saved.
That's right.
That's the requirement. We talk about science concepts which draw people in. Take these nanomachines and have them drill into cells. This would be a great way to kill cancer, right? We also talk about Jesus Christ, who's the best in everything. My faith in Jesus Christ means more to me than anything. If you could continue to give or give for the first time, we would certainly appreciate it. You can go to jesusandscience.org. Thank you so much.
So let's say that you start off with a certain amount of glycine. The amount of glycine here doesn't really change much because if you at equilibrium, the amount of peptide formed is so small that in your own thinking, it doesn't matter if you say the initial concentration of glycine or the equilibrium concentration. It works out about the same anyway. But the bottom line is the following. Origin of life people have different opinions on what would be a reasonable concentration to assume initially for amino acids altogether. Okay? And we're talking about glycine because it's so dominant that it doesn't matter if you say glycine or all the other amino acids put together. But in the literature, you'll see values, estimates ranging from 10 to the minus 4 molar to 10 to the minus 10. Now that makes a huge difference on the concentrations that result, which is obvious because look at the intermediates. In order to go from, let's say, a dipeptide to a tripeptide, it requires the amino acid itself at every step. So if this is very, very high concentration initially, then all of the larger peptides are going to benefit from it. That's why these models show exactly what we knew was going to happen. The predicted concentrations at equilibrium, which is look at what happens here. That is the highest concentration, right? The highest concentration of any of these peptides will be at its equilibrium, back and forth, not during the process of forming the peptide. Just wait long enough, typically about 5,000 years at the most, at 25 degrees, and you reach equilibrium. What concentrations are we getting for peptides? Well, obviously, less and less and less and less, the larger the peptide gets. I underlined 3 important values because these are the concentrations that we would need for the kinds of peptides used to form amyloids. Remember we talked about 4 to 7? That would be an extremely optimistic example. So for our thinking, let us be as favorable as possible to an evolutionary scenario. We will assume the highest concentration that I have found in the literature assumed for amino acids being produced, which is typically 10 to the minus 4 molar, okay? If that were to occur at equilibrium, then you would have a concentration of the octapeptide of about 2 to the 10 to the minus 45 molar. Now, remember, if you remember, we talked about the template peptide in some of the experiments. That was exactly 8 amino acids long, 8. So this is saying, don't worry for the moment about the particular sequence. Just any old octapeptide of any kind whatsoever. Its concentration in water at equilibrium, 25 degrees, is about 10 to the minus 45.
Can I translate this so we can move on? Because I think you're getting really, really detailed, and we have to move on. Basically, this is garbage. These reactions don't work. These origin of life reactions don't work. These concentrations are so low, they're utterly irrelevant. It's irrelevant. That's what this means. And so anybody to say something different is crazy. And if they say, well, we used hot, dry cycles in order to get this to move the water away. But as soon as you add water back in, it's gonna
Right.
go and reverse. So even
Exactly.
if you look at the things that Lee Cronin did when he used wet, dry cycles, the biggest he ever got were like 14 MERS, and these things are going to be cross-linking, hydrolyzing, and racemizing. So anyway, let's wrap up this slide. We've got to get through this because we're not going to get done here, Dr. Truman.
Right. Okay. So the studies that I use are this is some of the data that is available from the literature is showing you the free energy of hydrolysis. So for the dipeptide, it is minus 3.6 kilocalories per mole, and then the various peptide scenarios, whether you're breaking off only the end or in the middle, you've got these kinds of values.
And just let me mention that when the free energy is negative, that's a spontaneous reaction.
That's correct. So basically at 25 degrees plus or minus 10, the kinetics doesn't matter too much, nor does the free energy. You're not going to get peptides. Okay. What about under hydrothermal vent conditions? Now you got a different problem. Start off with amino acid from a dipeptide. The problem here now is that these things are unstable. They decompose very, very, very rapidly. Okay. And incidentally, not the topic today, but just keep in mind that racemization of the amino acids is a far more serious problem in peptides than amino acids.
Yes. So let me just mention here. What he's just shown you is if you want to say you make your amyloids in a hydrothermal vent, it's over. Game over. Game over. First of all, it doesn't favor the making of the peptide. It favors the depolymerization of the peptide, number one. Number two, if you did have any chirality there, the chirality is lost because it would racemize. Right. So this nonsense that these things are going to form for you in a hydrothermal vent is really nonsense. They're not going to form for you. The things that you might find today are biotically relevant. These things came from biology. They didn't start out that way. So this is nonsense that these guys are throwing out there. And they just don't know. The YouTubers don't know. The researchers are masking and hiding this.
Correct. The evidence is unambiguous. Based on the best work done to date on hydrothermal vent type conditions. Look at the temperature, 160 degrees. You're not getting any thing larger than a dipeptide. Again, always keep the time in mind here. So these are starting off here at an almost pure amino acid, right? To get anything here at all. So this is obviously not realistic, but that's not the point. The point is what happens. What happens in hydrothermal vents? Raise the temperature a little bit, you see CO2 blasting out. You're decomposing the amino acid, right? So you're still not seeing anything larger than a dipeptide. And now our friend time kicks in, you see what happens. It's very, very quickly starts to degrade, incidentally, just like Lee Cronin's peptides, also in the wet-dry cycles.
He didn't report the degradation, nor did he report the racemization.
But you see it. You see it
He never reported it. He did HPLC or ultra UPLC, and he just said, "I have these peaks here." He didn't characterize the peaks. He didn't ever show if they had racemization, nor did he discuss decomposition. It was all a scam.
Right. And right. I agree. I wrote a paper about it myself. On precise those experiments. They don't show, they claim they show. But that's a different topic at the moment. Let's raise the temperature again. Now, at 260 degrees, you are, if you do experiment very carefully means a very special reactor, very high concentrations, you do get some peptide. It reacts so quickly, if you blink, you've missed it. You're talking about literally in the second, and it's gone. CO2 goes up, dipeptide goes down. So bottom line is you're not going to get
Okay, so
large peptides.
this is such beautiful data, and I wish that the audience could appreciate this. I'm afraid they're not going to. So let me just tell them.
Go ahead.
That you got to to make a realistic peptide, you got to put like 300 together. If you want to talk about amyloids, okay, so you want to talk about putting 10 together, and you want to say this formed in a hydrothermal vent. Here's the hydrothermal vent temperature experiment. If you do it at 160 degrees, you never get more than 2 put together. That's it. And if you do it at 220 degrees, you only get 2 put together, and they start decomposing. They start falling apart to CO2. If you go up to 260 degrees, now some of these vents can be over 300 degrees. So you get to 260 degrees, you form a trimer, 3 of them, but it decomposes so quickly. Right after it forms, it decomposes, and it just falls apart. There's the decomposition. So the whole hydrothermal vent synthesis of polypeptides is gone. Game over for this. Game over. You can stop talking about it. You're going to have to deal with this data. If you want to say the polypeptides formed, that these amyloids formed in a hydrothermal vent, this is what you've got to deal with. Somehow you've got to deal with this data. You're wrong. It's not going to happen. Dr. Truman is correct. Here's the data. So anyway, that's the bottom line of it.
Correct. If anybody wants to have a little bit of fun, I misspelled the word optimizing. Even this is highly optimized. That meant you have removed all impurities that are known to catalyze the degradation. And this particular one, this study was actually done in literally, don't laugh, a gold-plated reactor. Anything possible to remove all of the known impurities to even obtain these results. Normally,
yes,
it's far worse.
And here, they're saying that the hydrothermal vents can be basic or they can be acidic. Base or acid is going to make this decomposition
worse.
Go much worse.
Right.
And any metal salts. I mean, these hydrothermal vents, this is stuff coming up from under the ground. Any
minerals.
metal salts. These things are full of metal salts.
Right.
Particularly divalent salts like zinc or magnesium. You remember, 2.5% of the surface of the Earth is magnesium. Magnesium atoms is going to make this even more difficult to happen. It's going to give more problems for your explanation. So this is why I say this is the data. This is the data that shows these experiments, these origin of life researchers are putting forward, show that it doesn't work. And when chemists look at it, they can figure it out. Go ahead.
That's correct.
Dr. Truman.
Now, there is this elephant in the room, and something that I kind of enjoy thinking about. Remember now, we said that the concentrations of peptides independent of the sequence is very, very low. This is a particularly interesting value because it's easy to remember. An octapeptide, this concentration works out to about 1 peptide in all terrestrial water. Just, the liters of water on Earth, Avogadro's number, easy to figure out.
So 1 peptide in all of terrestrial water.
Right.
That means in all the oceans and all the water bodies of the Earth, you would have 1 molecule.
Right.
1 molecule. That's what that concentration works out to be.
Correct. Is the most optimistic scenario possible. You're starting off with a very, very high concentration amino acid, no impurities, no side chain branching that would shorten the peptides, etc. Well, even this is hopelessly optimistic, but this is the number. Now, here's the thing now. The elephant in the room, which nobody seems to want to mention, is that you need now identical peptides. That means from this concentration now, you've got to have trillions of identical within a milliliter to form amyloids. So the wet-dry cycles that you mentioned is not a solution for many reasons. I wrote a couple of papers on this. First of all, if you were to remove lots of water, let's say a factor of 100 and keep on going down, you're going to concentrate everything in water. Water is not 100% water plus amino acids. Imagine what would happen if you were to remove 99.99999% of salt water to try to concentrate the amino acids. Well, you've got sodium chloride, 1,000 other things in there. So you're going to end up with a cement slurry. You're not going to end up with, peptides.
And salt water isn't just sodium chloride.
Right,
There's dozens of different
exactly.
cations and anions in there.
Right. And wet dry cycles, I saw Lee Cronin's paper. If you look at it very, very carefully, it is actually destroying. If you go from cycle 3 to 4, it's actually decreasing the concentration of the larger peptides simply because you're destroying the starting material. And of course, the obvious problem is how do you keep the stuff from simply remixing? Anyway, anything you do to concentrate peptides is either going to solidify solid as cement someplace, which means they're worthless for origin of life purposes, or they're not solidified solid and worthless. They remix in water. If they remix in water, they're going to hydrolyze and remix, with everything else. So you don't have a solution here. So I'm interested now in this issue about how the world are you going to get these special peptides. Now, remember, these are the concentrations of the peptides we talked about in our last talk. 10 to minus 4, 10 to minus 2 molar. They have to be or they don't form amyloids at all, especially when they're that short. When they're 4 to 7 amino acids, they've got to be extremely concentrated or they're not going to form, the beta sheets and the amyloids at all. So these things were done as shortly as possible. Here's the issue. You've got an amino acid, 2 ends can react. And there are countless things that can react with carboxylic acids or with amino groups. There are the desirable proteonic amino acids, that's right, a whole bunch of non-biological amino acids, and all kinds of other stuff. These are kinds of examples that you find in meteorites or Miller type experiments. All these things are contaminants that could also react with amino acids. So you got all this interference. So the question is now, abiotically, what would have been present? You see, there's not too much of a difference in the stability of the bonds that form. They're all unstable. So whatever is present in greatest amount that can react at the carboxyl end or the amino end is going to do so. So the question is, what would have been present? Are you going to get the right kinds of peptides at all? Here are the results from a repetition of the original Miller-Urey experiment redone in 1959 using much better lab techniques. They got 4 amino acids and other things. Now, here's a message that I want you to take home with you. Glycine plus alanine is dominant. Then you've got 2 more amino acids in very, very small proportion. These are now non-proteinogenic amino acids. Notice that this value here is 26 times more than all these 18 other amino acids here put together.
So in other words, the non-relevant amino acids are 26 times higher in concentration than the relevant ones?
Then the 18 ones, once you exclude glycine, which is virtually everything,
yes,
plus aniline, that's correct.
Glycine and aniline, right.
And of course, you've got
everything else is just such a trace.
Exactly.
Oh, boy. So this experiment is even worse than what I've been saying in the sense of being useful. I mean,
but this is important because we have to understand realistically, pretending that we believe in evolution, we have to understand what is realistic, what would have been expected. In this experiment, they also identified...
You just said something, we believe in what?
Evolution, that we believe in a naturalistic...
Okay.
Right.
If we go under the assumption that it's entirely naturalistic, then we've got to deal with this. Okay.
Exactly. We have to know the data. Yeah. We have to know the data.
Right. Okay.
And here are the carboxylic acids that were measured in the same experiment. This is, of course, vastly more than everything else all the amino acids put together. They didn't measure other things like amines and other things.
If you look at the amount of carboxylic acid that's there, It's so much higher than all these other things put together. So that's going to, you could, in other words, what he's saying is the Miller-Urey experiment, what it generated would be totally unusable. Not only was it all racemic, but just the mixtures made it totally unusable. And this is what you find in meteorites as well. It's always unusable because of the competing molecules. It's unusable. And nobody wants to believe me, but this is the problem. It's unusable.
So what people do is they do exotic experiments and say, hey, guess what? I found a little protein. I'm saying, guys, let's come on, slow down a little bit. Look at the proportions. That's what we care about. So this is a very important experiment, and the message so far is 99 to 9.9% of those proteinogenic amino acids formed. Let's ignore everything else. Of those formed, they're exclusively glycine and alanine. Okay, that was that experiment. Other experiments are showing the same thing. They are using reducing gases here, meaning things like methane, ammonia, hydrogen, the things that you need to form amino acids. All of these experiments, you can look at these experiments also that I documented in one of my papers. They all show the same thing. They're showing that the primary product is almost exclusively glycine and sometimes a little alanine. But here's an interesting observation. People play with gas mixtures to see if they can optimize the amount or quantity or variety of amino acids. For example, if you don't have a sulfur source, then two of the amino acids that you want can't be produced. Methionine, I'm getting tired here.
Cysteine.
Cysteine, sorry. Right. So here's my observation. Anything you do to optimize the amount of proteinogenic amino acids produces an overabundance of non-proteinogenic amino acids. So that means, remember we talked about before this number down here, 26 to 1? Anything you do to try to get more of these or greater variety of some of the more exotic amino acids ends up increasing this proportion. This makes matters worse. What about other experiments? It's important to understand that the original Miller experiments using gas mixtures that are believed not to have been relevant anymore to the early Earth. And therefore, all kinds of other mixtures are played with. And here are a summary of some interesting examples. First of all, in these experiments, these authors are not claiming that these gas mixtures are realistic. They're just saying, let's see what happens if we try different mixtures, okay? Now, here's the bottom line. It's believed that the early Earth would have, the atmosphere have consisted almost exclusively of CO2 and nitrogen. Methane, forget it. Hydrogen it just disappears in space. So that is a big, big problem. But people, they play around with different mixtures, see what happens. Let's look at these experiments here. Most interesting would be example number 5 here. Here you've got a high proportion of hydrogen to CO2, far, far, far higher than realistic, which the authors admit. But, you want to see something, right? You want to see something at all. Based on the amount of carbon consumed, we talk about a yield of 100% of the amino acids, basically. So the yield is 0.01% using this mixture. Obviously, if you increase the hydrogen, you get a higher yield. That means that you can now extrapolate in the other direction, extrapolating down to what is more realistic, which is nitrogen and CO2 plus hydrogen coming from water, but not hydrogen coming from hydrogen itself, means you end up with a yield of pretty much zero. Okay, but the point is still the same. In all these different mixtures, you find that glycine and alanine together is everything. Everything else is just a trace amount. That's the message. Now,
So in other words, everything that people have tried to do to make it better has only made it worse?
right, what they report is, with great excitement, they found a peak that looks like it could be whatever, histine or whatever, okay?
Yes.
But what they don't do, typically they don't report or study the other components. And when they do, it turns out that far more of the undesirable contaminants are being produced.
Uh-huh.
So,
Okay.
so look at that.
Yeah.
So in other
So
words,
it's a-
you
yeah.
end up with 1 ppm of a cool amino acid you want, but now you've flooded the biosphere with all kinds of garbage you don't want. You're
Right,
worse off.
right,
You're
right.
worse off. So now, just when we saw things were getting bad, the bottom fell out here a couple of years ago, and that is some chemists suspected there was something wrong about about the original experiments entirely, and the suspicion was that the glassware being used by Miller-type experiments is catalyzing these reactions. These reactions, remember,
Which
are
happens all the time. I mean, glassware
know.
catalyzes reactions. Yeah.
Exactly. But these reactions are supposed to happen in the atmosphere, not surrounded by glassware. So some clever people did really one of the best studies I've come across yet.
What did they do?
They used Teflon here. But I
Okay.
say best because they actually bothered to look at all of the components coming out.
Okay.
Everybody else looks at, they report what they want to find, but they don't report what they don't want to find. And it's kind of like, for what? But here they actually went and did some pretty systematic work. So what do we see here? Glycine, they couldn't find any. Alanine, none. Valine, none. Basically, they got almost no amino acid, but astonishingly, they did get quite a bit of non-proteinogenic amino acids.
So what he means by non-proteogenic, he means that the ones that are not involved in life.
Exactly.
Yeah.
And you get a whole lot of other stuff that you don't want.
Okay. That's amazing data. I didn't know that, but
Right.
I could see that happening.
Right. Now, to be sure that you're properly amazed, they deliberately selected an ideal gas mixture because they wanted to see something at all. So they went with, they went with about the best theoretical mixture to form amino acids humanly possible, knowing full well that's got nothing to do with origin of life. So they went here with ammonia, methane in particular. So that means that if they had gone down to anything remotely realistic, they would have found 0.000 of any amino acid.
Did he, in his paper, I've read the Miller-Urey paper. It was very short. He didn't tell us, I don't know, remind me, did he ever say how many reactions he ran in order to get that?
Yeah, this was back then when TLC was used for analysis. This is really back in, mid 56, I think. The issue here was, no, I think he only did it once, but he did repeat many experiments over the years later and didn't analyze all of his samples. Some people analyze the samples years later.
Yes.
But he uses gas mixtures that were optimized for amino acids because other origin of life people like Operem had recommended that, not because it was geochemically plausible, but because it would be plausible for origin of life purposes. So basically, he used gas mixtures that are not believed to be relevant anymore.
Okay.
So basically, you got a big problem here. So interesting that in this experiment they didn't repeat the Teflon work with more realistic mixtures, but every chemist knows anyway what would have happened.
Yeah.
If why bother? I mean, you're not going to get anything whatsoever. The Teflon reactor experiments showed that there were substances in the glassware that was catalyzing these gas reactions that would not have occurred, of course, in the early atmosphere. And without that, we wouldn't be getting any amino acids or just in insignificant amounts at all. We would still be getting all the wrong substances, including lots of carboxylic acids. I mentioned that they used the ideal gases, CO4, ammonia, to produce amino acids because they wanted to see something at all. And that's not entirely bad because people are constantly looking for a way out or an explanation for all these dilemmas. And one includes the theory there may have been one or more huge impactors in the early Earth, which slammed into the Earth and evaporated all the water with such heat that the water is converted into hydrogen. And the idea is perhaps methane and ammonia plus hydrogen plus enough iron could have been produced maybe to do something useful. So what I'm trying to do is produce a total picture of what the real realities are and whatnot, so that one doesn't spend too much time on looking for all kinds of exotic models where absolutely nothing works. Here are the results from what I believe are the most detailed studies ever done on the Murchison meteorite, which is the best studied meteorite in the land of Australia. And it is representative of those few, the minority of meteorites that actually have amino acids with them. The bottom line is, surprise, surprise, glycine is a dominant from among the amino acids. Then you get a bunch of non-proteinogenic amino acids following in concentration, until you finally get down to alanine, then you get a bunch of other things. Now, it is commonly, everybody acknowledges this contamination. Nobody questions it. And unfortunately, the contamination would only affect the proteinogenic amino acids. That means they could have come from the immediate environment during the landing or during the decades of processing afterwards. But that's not true of the other substances. That means everybody knows that the amount of amino acids that are being measured are the proteinogenic ones are too high. But the point is just the same. Dominant amount of glycine and alanine from among all of the amino acids that you want to see. Now here is a recent paper, and this again could be a game changer. Very, very significant. Actually, very, very, very good work. Also very objectively done. Here's the bottom line. Some very clever Japanese fellows led by Kobayashi, they suggest that of all of the possible sources of amino acids, virtually all that have been proposed are irrelevant. The energy provided is too low, and that one should be concentrating on only 3 possible sources, of which 1 or 2 are all that really matter. Their argument is, okay, solar energetic particles, very high energy, and or galactic cosmic rays. These would have the energy level potential to split nitrogen and potentially produce amino acids in the atmosphere. And the third contributor would be our familiar lightning. So the argument is, well, a lot of SCP could have been created from massive solar super flares. That's the idea. So they did some work in a tandem accelerator, high energy beam, proton beams because SAPs and GCRs are primarily exactly that, protein beams, and they would be able to split CO2 and nitrogen. So, and that's good because they finally decided to do some work with realistic atmospheres because for the first time, that might actually do something useful, something interesting because of our energy source. Now, very, very important and critical to the results is the amount of methane, the proportion of methane involved that has a dramatic effect on the results. Now, they admit freely what everybody pretty much acknowledges, and that is the proportion of methane in the early atmosphere would have been less than 5%. It'd be very, very low. Okay? Let's look at the results now. Let's go to the table. This, the RCH4, that is the proportion of methane. So let's look at the two columns that matter, 0, 5%. And then everything else is CO2, nitrogen, and water. So what are we getting? The concentration here are in units of billion moles, tens of moles. These are the units. They're getting almost only glycine, tiny amount of serine. There could be a little of aniline that is simply not seen in the tiny, in the massive glycine peak. And lo and behold, once again, vastly more non-proteinogenic amino acids than everything else once you exclude glycine. So now things are really dramatic. Now we're not talking about 99 to 99.9. Now you're talking about 99.99 or more percent glycine flooding the biosphere. Mm-hmm. So if you get an amino acid, you're getting glycine. So
let me just tell people, glycine is like the simplest amino acid. It's got no functionalities hanging off of it. You can't do any catalysis or anything with glycine. And what he's saying is that in the original experiment, it swamps the system. In this experiment, it's the only thing in there that's of relevance. And you can't get methane that high in the atmosphere to give you anything relevant of anything else. And even the Miller-Urey experiment, if you didn't do it on glass, it wouldn't have worked anyway. So there's just so many things that are battling with this.
Right. Don't forget, Dr. Turner, don't forget the glycine doesn't have a racemic center. So it means you could never form a protein. You can never form a peptide that can fold properly.
Yeah. Glycine has no stereogenic center.
So it's worthless. So that is the bad news, and it just gets worse. What about non-amino acids? Now we're back to our friendly carboxylic acids. Now you're swimming in carboxylic acids. So even with zero methane, you're still flooding the biosphere with carboxylic acids.
This is what I said. All their reactions had to have been contaminated, but here the thing that's contaminating it is a carboxylic acid, which makes it so that you could never get the coupling of these things because it's swamped with a useless carboxylic acid, namely formic acid, just swamping the system, and acetic acid and propionic acid. So you look at these three acids, there's so much higher concentration than the other things that this is an unusable mixture. What was made is unusable, and everybody's writing to me these days, oh, look what they found on this meteorite. Look what they found on this. First of all, it's all racemic. Second of all, it's an unusable mixture. It could never be relevant. It could never be good for anything. And people still, well, it'd be all right. No, it won't be all right. Any chemist who actually has done bench chemistry understands that you can't do chemistry like this, especially when you have numbers like this that are very high versus very low things.
So the message is the kinds of substances that one would expect to find abiotically, whether they're peptides or similar reactions, are going to be based on what was available, what's going to react. So are we going to get these kinds of peptides? Like, for example number one, we talked about there are the best and the shortest, most clever peptides used that were capable of forming amyloids, okay? These relied on things like lysine and aniline at best in trace amounts. Trace amounts, I'm being generous, okay? Let's say you had 1 billion times less than glycine, okay? You see the problem here. How are you going to get any of these materials when
they're not going to
everything else
form
happens?
when you have
Exactly.
such high concentration of glycine around. Yeah.
Look at the other example. Here you've got, remember we had an example here with a bunch of histidine. Same thing. These things are extraordinarily rare, not to mention the other problems that you alluded to, like zinc and whatnot. Things get even worse now when you require two peptides of unrelated sequences, both of which rely on trace or non-existing amount of amino acids, both being present concurrently to form beta sheets, as the most famous, most talked about series of experiments by Root et al. And Murray came up, spent probably years coming up with something actually quite remarkable, quite clever. He came up, found a nonapeptide, which used some of the more common, so to speak, amino acids. But he had to use a pretty high concentration to get the peptides. So let's just take a look now at what this means mathematically. The key here is what would have formed. You've got a carboxyl end. It's going to react with whatever things carboxylic acids react with at this end here, okay? All kinds of stuff. Alcohols, amines, all kinds of stuff. And the same at the other end, okay? So the question is, if you had an amino acid or that peptide, what's going to form? So when you look at scenario number one, let's look at Murray's example, which is interesting because he could argue that maybe originally there were fewer amino acids, not all 20, but maybe only 10. This is commonly proposed in Origin of Life. It's called a reduced amino set. If there are only 10 to compete against and not 20, then it might be easier to form this kind of a sequence because there are less amino acids, that would be able to show up. That's the argument. But do your calculations, come up with any guesstimation you want. Take into account that there are other substances like hydroxycarboxylic acids that you don't want. They're very similar to amines and stuff. Glycine is going to be in high proportion, in high proportion, but eventually you're going to have to admit that you rely on some amino acids low proportions. So you end up with values that are very, very low, like 10 to the minus 18, of which less than 1% would be L only. Okay? So the first message is, how in the world are you going to get identical peptides of any kind in large enough concentration? And how many peptides would have been available at all of any sequence? Well, the computer simulations showed that for a nonapeptide, you're talking about a number like this. That means one nonapeptide in 100 million oceans. So if you had one peptide, 100 million oceans, of that, this proportion would have the right sequence, but even that would not be good enough because it would be a racemic mixture. So it just gives you a feel for how fathomlessly far away we are from anything realistic. And that is true of any of the scenarios you look at. If you look at the shortest possible peptides, because you could argue, well, they don't have to be so long. Maybe they don't hydrolyze so fast, whatnot. The trouble is, these shorter peptides rely on ever more exotic amino acids because they've got the rich side group. They got exactly what you need to be able to form the amyloids. So now you end up with, like what proportion of all the substances floating around that would be of this length would, be appropriate. And that's, of course, ridiculously low again. And so on and so forth. All the other examples are even worse because now it's the worst of all worlds. That means now you end up with things that are 8, 9, 10 amino acids long, plus a whole bunch of non-existing or trace concentration amino acids. It just doesn't work. So maybe just one last slide, comments. There are a whole bunch of other things that nobody's ever mentioned before. Like we said that the concentration of larger peptides would be very small, but they would be in competition and present with peptides that are, let's say, one amino acid smaller and it two smaller. It'd all be like a big mess. You could try to concentrate the stuff by evaporating it, but what do you end up with? You end up with a ratio like 10 to the 12 to 10 to the 6 to 1 of this shorter peptide to this slightly longer one to the one you want. So you end up with this mixture here. And the larger peptides, if you could form it and if you could concentrate it, wet, dry cycle, anything you want, they're never going to find each other. It just doesn't change at all the proportions. And it just gets worse the more realistic you are. So again, there's a German expression, you've got to die somehow, okay? That means there are no good options. Without water, of course, there's nothing to discuss anymore. The stuff is not soluble, it's caked into stone. Don't talk about it anymore. If you want water to form amyloids, then the stuff hydrolyzes, and now the peptides of the right length are a mixture, an insignificant mixture and proportion of the slightly smaller peptides. So, these things don't go around looking for each other, floating across oceans. And this is very important. I don't want people making this mistake. You can't say these things might have built step by step. That's not right. Two peptides on the order of 4 to 9 amino acids, their interaction together is far, far too weak to have any relevance. Hydrogen bonds they don't do anything. They don't stick together and then go around looking for a third and a fourth partner. They just float apart again. So it's like crystallization. You've got to have a synergy effect. You've got to have a huge concentration together, and then eventually, poof, it all happens at once. We're talking about 10 to the minus 2, 10 to the minus 4 molar, identical peptides before you can form amyloids. So basically, you can forget the whole story. These things never existed. I'll show this slide in case anybody wants to look at the references.
Okay.
Because I've also got the URLs. So these are all the papers that I wrote on this one topic.
Well, it's hard for them to get those URLs, but they have the papers. You just Google those papers and
right, exactly.
It'll come up.
Okay, questions.
All right. So I mean, basically, what this is the amyloid hypothesis is dead. It is just dead. Everything has been, as you showed, a knockout blow at the end. I mean, everything. The concentration. You have one molecule in a bazillion oceans. The ability to copy itself, it can't do that. The ability to form in these hydrothermal vents, it can't do that. It's over. So this amyloid hypothesis, it's like many of the other hypotheses. They just all fall apart. And remember, when you're talking about the life of a typical polypeptide in water, the things hydrolyze. You bring it up to the high temperatures to get it to form, the things racemize. Lee Cronin's experiment was meaningless because he never checked racemization. He never checked the decomposition products that were blowing out CO2 and forming at these higher temperatures. He was using these temperatures, well over boiling temperatures, well over boiling water temperatures. And so you're just going to get to see these decompositions. This is what's happening. It's just like I said, the very experiments on origin of life scream out that it didn't happen this way. Life didn't happen this way. It happened somehow. But as far as scientifically what we know, we have no idea. This is why I keep saying we are clueless on the origin of life. And everybody says, "Oh, no, we're not clueless." What are we confident about? What are we confident about? Are we confident in any of the small molecules? If you say that yeah, there's amino acids, but they're always racemic. And they're dominated by many other compounds and surrounded by many other compounds that would be useless anyway. And if you look at the amino acid concentrations, it's almost all glycine and alanine. And so that would swamp out everything else. And if you want to say, and then there were all other competing things. And then plus you couldn't get these to couple without doing the blocking, which these people did and they never talk about. And you want to go to the sugars? You know how hard it is for sugars to form? If you want to say the foremost reaction, the foremost reaction makes billions of compounds. And so it would be, again, unusable because you wouldn't have a high enough concentration to use these. You want to say nucleotides? Nucleotides have to solve the sugar problem. It's never been solved. Nucleotides have to, RNA has to solve the 3'5" only linkage rather than the 3' 5' rather than the 2' 5' linkage. It's never been done. It's never been done where you've solved the branching problem off of RNA. Never been done. So all of these are problems that we don't know how to address. And so, nothing has been solved here for us, and we can't make the polymers. And even if we could make the polymers, they wouldn't have the requisite information stored in the polymers. If we could get the information stored in the polymers and we had the polymers, then what? How do you get the cell to assemble? Just making a lipid bilayer doesn't do it. Just making a vesicle doesn't even do it. You have to have proton channels, proteins in there for proton channels to go through, for ion channels to go through. And then you have to get all the assembly in the cell. Just throwing all the car parts into a pile and shaking it together, it's never going to come together. Every one of these is an insurmountable problem based on what we know today. Based on what we know today, we have no idea how life formed. So you can bank on that. What do you say to that summary, Dr. Truman?
Yes, it's a good summary. I chose to talk about polypeptides and amino acids today because it's easier. Everything you said in your summary is true, and even more true with RNA and DNA. Everything. For example, I said that polypeptides hydrolyzed in water is even more exothermic for both RNA and DNA. It's worse. I talked about the branching problem, the side chain. The problems you've got with all the stereochemistry that can occur with RNA and DNA is 1 billion times worse. So everything I've said is true, but far, far worse with RNA and DNA. So my personal opinion is you've got to have a super chemist. You've got to have an intelligence that is somehow planned and organized. These things just don't happen by themselves. That's not what the chemistry shows.
Okay, and what would you say to someone like Sarah Walker, who's an astrophysicist, who says that Jim Tour just puts up straw men, that the chemistry is a straw man? Don't even worry about that. What would you say to that?
I've got a 3-paper series waiting for publication, so I don't know if I can give you a short answer. But this whole thing, the assembly theory has got to translate, it's got to map somehow to chemistry. Their complexity index has got to say something about real chemistry to have any validity. She's a physicist. Jill Cron is an organic chemist. That makes life a little difficult when we say, what are you talking about? When I understand complexity theory. I've written papers and given lectures on Shannon information theory. I know these things. I know what complexity theory is. I know what compression is. I did more work as a computer scientist than as a chemist professionally. So I understand what they're saying. But my question is, what does this have to do with the origin of life?
Yeah, I don't see what it has to do with origin of life. If you want to say a complexity index, fine. I can look at a molecule. If you tell me you have 5 of those molecules where all the stereocenters are the same and it has a molecular weight of 1,000, I can tell you that it had a causal history. I can tell you that without having your silly little numbers that you put on it by blowing something up with a mass spec. But it's not going to tell me anything about the origin of life. And to suggest that chemistry is a straw man is really silly. Lee Cronin hasn't done that, but Sarah Walker has done that. And, I tried to talk with her about this. She would not meet with me. I was even at Arizona State University giving a talk. Long before I got there, I said, I'm going to be there on that day. Would you meet with me? She wouldn't respond. The host even contacted. She would decline. I said, how about, can I meet with one of your postdocs and we can discuss this? Wouldn't allow me to meet with one of her postdocs. So these people are really closed. They don't want to discuss it. They don't want to talk about it. And that should tell you something. How do you know the people that are not being honest about the data? The people that won't talk about the data with me. Those are the ones that are not being honest. That's how you can tell that. They want to silence it. The people that are trying to silence the conversation, they're the ones that are causing the real troubles here. So with that, we're going to wrap this thing up. This was a lot of technical information. For those of you that got through with this, man, you should get like a degree in something, a degree in fortitude for getting through this. But that's the chemistry. That's what you got to deal with. Dr. Truman, thank you so much. I appreciate it. And if you could, I guess my producer has that list of papers. So what he'll do is he'll take that list of papers, he'll put it in the description box, so you can just look below and you'll see in the description box that list of papers. If it gets too long, he'll give a link to that list of papers so that people can get it, and also the URLs. And you've published in this area a lot, so people can't come at you and say, well, you haven't published in this area. You've published a lot in this area. So good for you, and thank you for joining us.
My pleasure.
Thank you for joining me today. If you could give us a like, share, or podcast review, we would appreciate it. If you have any questions, you could send them to ask@jesusandscience.org, and we'll try to answer some of those questions in an upcoming video. And if you do not believe in the physical resurrection of Jesus Christ, and you want to hear about why I believe, send me an email to tour@drjamestour.org, and we'll get together by Zoom, and I'll share with you why I embrace the resurrection of Jesus Christ.